This is Physics 2120, Lecture 21, and today we're going to go through alternating current circuits. So an AC circuit consists of a combination of circuit elements and a power source. And the power source is going to provide an alternative voltage, delta V. And the notation here is lowercase symbols are going to indicate an instantaneous value, and capital letters are going to indicate fixed values. So the output of an AC power source is sinusoidal and varies with time according to delta V is delta V max sine omega t, where little delta V is the instantaneous voltage at any time, and delta V max, the capital V, is the maximum output voltage of the source, and omega is going to be the angular frequency of the AC voltage. The angular frequency, omega, is 2 pi f, or 2 pi over the period. F is the frequency of the source, and t is the period of the source. The voltage is positive during one half of the cycle and negative during the other half of the cycle. The current in any circuit driven by an AC source is an alternating current that varies sinusoidally in time. And in the United States, commercial electric power plants use a frequency of 60 hertz, which corresponds to an angular frequency of 377 radians per second. So now let's look at what different circuit elements do in an AC circuit. We're going to start with a resistor. So the AC source is symbolized by this symbol here, and we know that delta V in this case is going to be the same as the voltage across the resistor. So delta V sub R refers to the instantaneous voltage across the resistor, and it's just delta V max sine omega t. The instantaneous current in the resistor then is the current at any instant is the voltage across it at any instant divided by the resistance, or delta V max over R sine omega t, or in this case it's just I max sine omega t. So the instantaneous voltage across the resistor is also given by I max R sine omega t. This graph then shows the current through and the voltage across the resistor. The current and voltage reach their maximum values at the same time. So the current and voltage are said to be in phase with each other. They both vary sinusoidally. Their peaks and troughs occur at the same time, so they are in phase with each other. For a sinusoidal applied voltage, the current in a resistor is always in phase with the voltage across the resistor. The direction of the current has no effect on the behavior of a resistor. So resistors essentially behave the same way in both DC and AC circuits. Now, one of the things we can do in an AC circuit analysis is use something called phasors. And a phasor diagram can help us understand what's going on. A phasor is a vector whose length is proportional to the maximum value it represents. That vector then rotates counterclockwise at an angular speed equal to the angular frequency associated with the variable. The projection of the phasor onto the vertical axis represents the instantaneous value of the quantity it represents. So if we were to allow this to change in time as this were to go, the projection of this phasor on the axis would increase, and then it would decrease through zero and then go negative, and it would show us the instantaneous value of voltage or current across the resistor as a function of time. Now, as we try to get some ideas of how to talk about the circuit, the average current might be something we could talk about since it's changing, but the average current of something that's varying sinusoidally is always zero. So instead we use something called the RMS current. It stands for root mean square. And this is the average of importance in an AC circuit when we're dealing with things. So essentially what we're doing is we're squaring the voltage or the current. We're taking the average of the square and then take the square root. And if you do that, the RMS current is always the maximum current divided by the square root of 2, or 0.707 I max. Alternating voltages can also be discussed in terms of RMS values. Vrms is the maximum voltage over the square root of 2, which is 0.707 Vmax. When I'm measuring voltage of an AC circuit with a voltmeter, typically what I'm measuring is the RMS voltage. Now then, the rate at which electrical energy is dissipated by the circuit is given by P is I squared R, where little I is the instantaneous current. So power is being dissipated at a changing rate in the circuit. The heating effect produced by an AC current with a maximum value of Imax is not the same as that with a DC current of the same value, because that maximum current occurs for only a very small amount of time. However, I can talk about the average power delivered to a resistor that carries an alternating current, and that is I RMS squared times the resistance. Now again, RMS values are used when talking about AC currents and voltages because AC ammeters and voltmeters are designed to read RMS values. And many of the equations that will be used have the same form as their DC counterparts if we use RMS values. The next circuit element we want to talk about is an inductor, and we can use Kirchhoff's rule to look at what the voltage in an inductor looks like. If we go around here, we have delta V of the source plus delta V of the inductor is equal to 0, or delta V is equal to minus L di dt, well, that's the instantaneous voltage, or delta V is equal to L di dt, and we know that delta V is delta V times sine omega t. So, given this equation from the last slide, we can integrate to figure out the current across the inductor. So, we divide both sides by L, we multiply by dt, and we integrate, and so we're going to get the current through the inductor is delta V max over L times the integral of sine omega t, which is minus delta V over omega L cosine omega t. Or getting this cosine back in terms of a sine, it's I is delta V over omega L sine omega t minus pi over 2. Where I max here across it is the maximum voltage over omega L. It shows us that the instantaneous current in the inductor and the instantaneous voltage across the inductor are out of phase by pi over 2, or by 90 degrees. So if I were to plot the voltage across an inductor and the current through an inductor, we see that here in this graph they're out of phase. The current in the circuit is impeded by the back EMF of the inductor. So for a sinusoidal applied voltage, the current in the inductor always lags behind the voltage across it by 90 degrees. In other words, if I apply a voltage across it, when the voltage reaches a maximum, it's 90 degrees later that the current actually reaches a maximum, when the voltage actually is at 0 from the driving AC voltage. So the phasors for the voltage across an inductor and the current through an inductor are 90 degrees out of phase with each other. That represents a phase difference between the current and the voltage. Specifically, the current is 90 degrees behind the voltage. Remember behind because these things rotate around, and so as this vector crosses maybe this axis, this one's going to, at 90 degrees, or when omega t is 90 degrees out of phase. So that factor omega L has to have the same units here as resistance, and it's related to current and voltage in the same way as resistance is. Because omega L depends on the frequency, it reacts differently in terms of how it offers a resistance to the current at different frequencies. And so we have a factor, we call it the inductive reactance, and that's chi sub L. This is the Greek letter chi, looks like a capital L, is omega L. So current can be expressed in terms of the inductive reactance. The maximum current is the maximum voltage over the chi sub L. So as frequency increases, the inductive reactance increases, which is consistent with Faraday's law. The larger the rate of change of the current in the inductor, the larger the back EMF, which gives an increase in the inductance and a decrease in the current. The instantaneous voltage across the inductor is minus L di dt. We figured out what I was, so we take the derivative. It's minus V max sine omega t, or minus I max chi sub L sine omega t. So next, let's look at a capacitor in an AC circuit. So in this case, we use Kirchhoff's rule again, say the delta V of the power source plus delta V across the capacitor is 0. And delta V is equal to delta V the capacitor, which is going to be delta V max sine omega t, where delta V sub c is the instantaneous voltage across the capacitor. The charge on the capacitor, Q, is CV, so that's going to be CV max sine omega t. And the current in the capacitor is dQ dt, which is going to be omega c delta max cosine omega t. Or getting this back in terms of a sine function, the current in the capacitor is omega c V max sine omega t plus pi over 2. So the current is pi over 2 radians, or 90 degrees out of phase with the voltage again. In this case, the current reaches its maximum value 90 degrees or a quarter cycle sooner than the voltage reaches the maximum value. So the voltage across the capacitor lags behind the current by 90 degrees. So the phasor diagram then shows that for a sinusoidally applied voltage, the current always is ahead by 90 degrees of the voltage across the capacitor. It's equivalent to saying the voltage lags the current. The maximum current in the circuit occurs when cosine omega t is equal to 1, which gives I max is omega c delta V max, or delta V over 1 over omega c. So the impeding effect of a capacitor on a current in an AC circuit is called the capacitive reactance. And chi sub c is 1 over omega c. And then we have something that looks like Ohm's law. I is equal to V over R, or I equals V over the capacitive reactance. The instantaneous voltage across the capacitor then can be written as delta V max sine omega t, or I max chi sub c sine omega t. So as the frequency of the voltage source increases, the capacitive reactance decreases and the maximum current increases. So as the frequency approaches 0, chi sub c approaches infinity and the current approaches 0. This would act like a DC voltage and the capacitor would act like an open circuit. So now, we've looked at what each individual one looks like. What if we put them all together? The resistor, inductor, capacitor series circuit for an AC circuit source. The current in the circuit is the same at any time and varies sinusoidally at time. I can't have current through this element and this element being different. The voltages are going to be different. And I know from Kirchhoff's rule, this voltage has got to be this one plus this one plus this one. But the current at any instant in time has to be the same through all circuit elements when they're in series. So the instantaneous voltage of the source is delta V max sine omega t. And the instantaneous current is given in the circuit by I max sine omega t minus phi. Phi is called the phase angle between the current and the voltage in the circuit. So since the elements are in series. The current at all points in the circuit has the same amplitude and the same phase. Now we know the instantaneous voltage across the resistor is in phase with the current, but the instantaneous voltage across the inductor leads the current by 90 degrees, and the instantaneous voltage across the capacitor lags the current by 90 degrees. So then if I were to look at these voltages across each one, since the voltage and current are the same on the resistor, we can use it as a kind of a placeholder. So in this peak, delta V sub L is going to be reaches a peak 90 degrees before that, and delta VC reaches a peak 90 degrees after this one. So the instantaneous voltage across each of the three circuit elements is expressed as, well, delta V sub R is I max R sine omega t, which we could just call delta V sub R sine omega t. And delta V sub L is I max chi sub L sine omega t plus pi over 2, or delta V sub L cosine omega t. And for the capacitor, it's I max chi sub c sine omega t minus pi over 2, or minus delta V cosine omega t. Delta VR is the maximum voltage across the resistor, and it's just I max R. Delta V sub L is the maximum voltage across the inductor, and that's I max chi sub L. Delta V sub C is the maximum voltage across the capacitor, and it's I max chi sub C. And in series, the voltages add, and the instantaneous voltage across all three elements, delta V, is equal to delta VR plus delta VL plus delta VC. Now, if we were to try to solve this and plug in the sines and cosines and minus cosines for all these, it could get complicated mathematically, and it's going to be easier to solve these circuits using the phasor diagrams. So we know that I max and delta VR were in phase with each other. In an inductor, the voltage leads the current, and a capacitor, the voltage lags behind the current. So to account for the different phases of the voltage drops, we're going to use these vector techniques, remembering that phasors are rotating vectors, and the phasors for the individual elements here are all shown. We put all of these on a combined phasor diagram. So we're going to use a single phasor I max to represent the current in every element, and in series the current is the same in each element. And then delta V, R, C, and L are all given by these phasors. And the vector addition of all of these is going to be delta V max. So we can combine the voltage of the phasors. Delta V, L, and C are always in opposite directions, so we can just subtract the two. The resultant is always going to be perpendicular to delta V sub R. So the phase angle here we can get from this diagram. So delta V max is the square root of delta V R times delta VL minus delta VC squared, or plugging in what this is in terms of current, it's going to be I max R squared. Then I'm going to get an I max minus chi sub L minus I max chi sub C. I can pull the I max squared out of all of this, and I get the square root of R squared plus chi sub L minus chi sub C quantity squared. So the current in an RLC circuit is I max is the maximum voltage over the square root of this function that and we're going to call the square root here something Z. Z is called the impedance of the circuit, and it plays the role of resistance in the circuit. Impedance also has units of ohms. So delta V max is I max Z. Now notice the impedance depends on the resistance, the inductance, and capacitance, but remember both these depend on frequency, so the impedance is going to change for different frequencies. So since I max is the same for each element, we can remove it from our phasor diagram, and the resultant is what we call the impedance triangle. So the impedance triangle confirms this function that we developed before, and it also can be used to find that phase angle phi. It's the arctangent of chi L minus chi sub c over r. So that phase angle can be positive or negative, and it really determines the nature of the circuit. We also can see that cosine phi is r over z. So if we were to look at all these circuit elements and put them in combinations, if we just have a resistor, the impedance is just R, the phase angle is 0. If we just have a capacitor, the impedance is just chi sub C, and the phase angle is minus 90, and with an inductor, it's chi sub L plus 90. If I just have a resistor and capacitor, the impedance is going to be square root of R squared plus chi C squared, and the phase angle is always going to be between minus 90 degrees and 0. It'll be negative. With just a resistor and an inductor, the phase angle is going to be positive between 0 and 90 degrees. If you have all three of them, then it can be either negative or positive, depending on whether chi sub C or chi sub L is a larger value. Now the average power delivered in a generator is converted to internal energy of the resistor. The average power is 1/2 I max delta V max cosine phi, or I RMS delta V RMS cosine phi. Cosine phi is called the power factor of a circuit. We can also find the average power just in terms of resistance. The average power is I RMS squared R. Now, we're using just a regular P for the symbol in these slides here because the symbol used for power that in our books is not available on all computer platforms. The average power delivered by the source is converted to internal energy in the resistor. No power losses are associated with pure capacitors and pure inductors in an AC circuit. In the capacitor, during 1/2 the cycle, energy is stored, and the other half energy is returned to the circuit, and no power losses occur in the capacitor. In an inductor, the source does work against the back EMF of the inductor, and energy is stored in the inductor, but when the current begins to decrease, the energy is returned to the circuit. The power delivered by an AC circuit depends on the phase. Some applications include using capacitors to shift phase around in heavy motors, so excessively high voltages are not needed to drive the motor. Resonance in an AC circuit occurs at a certain frequency we'll call omega naught, where the current has a maximum value. To achieve maximum current, the impedance must have a minimum value, and that's when chi sub L is equal to chi sub C. And if we use that, solving for the frequency gives omega naught is 1 over the square root of LC. That is the resonance frequency. It also corresponds to the natural frequency of oscillation in an LC circuit. So resonance occurs at the same frequency regardless of the value of resistance. And as R decreases, the curve becomes narrower and taller if I'm looking at the current versus the frequency. So in this case, omega naught is equal to 10. So if I were to, say have the driving frequency at 9, a maximum current I could get, let's say, in this green line is right here. But as I shift the frequency, I'm going to get higher and higher current. But then as I increase it past that resonance frequency, it's going to go down again. Now, theoretically, if R is equal to 0, the current would be infinite at resonance, but real circuits always have some resistance. But the lower the resistance, the sharper the peak. So then power can be expressed as a function of frequency in an RLC circuit. The average power is delta V squared R omega squared over R squared omega squared plus L squared times omega squared minus omega naught squared squared. Whew. What that really shows is that at resonance, the average power is at a maximum. When omega is equal to omega L, this term goes away, and the omegas cancel out, and I get a maximum power output at that point. Now, the sharpness of that resonance curve is described as a dimensionless parameter known as the quality factor. Q is equal to omega naught over delta L, or omega naught L over R, where delta omega is the width of the curve measured between the two values of omega for which P is at half of its maximum value. Those points are called the half-power points. A high Q circuit responds to only a narrow range of frequencies. It's a very narrow peak. A low Q circuit can detect a much broader range of frequencies, and typical Q values in electronics go from around 10 to 100. Now, a new circuit element that we can talk about in an AC circuit is something called a transformer. And an AC transformer consists of two coils of wire wound around a soft iron core. The side connected to the input AC voltage is called the primary, or the input. And we'll say it has N1 turns. The other side is called the secondary, or the output. It's connected to some sort of load or resistor and it has N2 turns. And that soft iron core is used to increase the magnetic flux and provide a medium for the flux to pass through one and into the other. Eddy current losses are minimized if I use a laminated core. So it's not a solid iron core, it's pieces of iron glued together. And iron is often used as the core material because it's a soft ferromagnetic substance and it reduces things called hysteresis losses. We're going to assume that we have an ideal transformer, one in which the energy losses in the windings in the core are zero. Typical transformers, though, have efficiencies between 90 to 99%, not 100%, but very close. So, in the primary, delta V1 is equal to minus N1 d flux dt. The rate of change of the flux, though, is the same for both coils since the magnetic field goes through both. So the voltage across the secondary then is minus N2 d flux dt. And again, the fluxes are the same. So if I set those two equal to each other, we can relate the voltages where the voltage across the secondary is equal to N2 over N1 delta V1. So when N2 is bigger than N1, the transformer is called a step-up transformer, as the voltage across the load here is going to be higher than the voltage across the source. But when N2 is less than N1, the transformer is called a step-down transformer, because then the voltage on this side is going to be lower than the voltage on this side. The power input into the primary equals the power output of the secondary, because I can't lose energy someplace. So the equivalent resistance of the load resistance when viewed from the primary is, so if I'm looking at the resistance across the primary, it's N1 over N2 squared times the resistance of the load. Now, a transformer can be used for lots of things, but one thing is to match resistances between the primary circuit and the load. This way, the maximum power transfer can be achieved between a given power source and a load resistance. If you have a high-end stereo, that technique is called impedance matching, and you want to make sure that you have speakers that are rated the same impedance of your amplifier. A rectifier is a circuit element that consists of converting an alternating current to a direct current. The rectifier is the converting device. And the most important element in a rectifying circuit is something called a diode. A diode is a circuit element that conducts current in one direction, but not the other. So, I have a transformer here. I have a primary input, and then I have an output. In this case, N2 is less than N1, so this is going to be a step-down transformer. And I put a diode in line here, and so it's going to allow voltage to move, or current to move in this direction, but not in the opposite direction. This triangle with a line here is the circuit symbol for a diode, and the arrow indicates the direction that the current can go through the diode. So because of the diode, the alternating current in the load resistor is reduced to only the positive portion of the cycle. So the solid line in this graph is the result of the voltage through the resistor, and therefore the current through the resistor. So it's part of the sinusoidal, then nothing. Part of the sinusoidal, and then nothing. This is called a half-wave rectifier because current is present only during half of each cycle. Now, if I add a capacitor to the circuit, then the capacitor stores charge during this part of the cycle and then discharges it during this part, and it acts to level out the voltage, so you almost get a DC power supply. The time variation in this circuit is close to zero, and it's determined by the RC time constant of the circuit. It's represented by the dotted lines in that graph. A filter circuit is one that uses to smooth out or eliminate a time-varying signal. So after rectification, a signal may still contain a small AC component. It's called a ripple. And by filtering, the ripple can be reduced. And filters can be built to respond differently to different frequencies. Well, let's look at an RLC circuit. An AC circuit has a given resistor, an inductor, and a capacitor. It's driven at the US standard. Omega is 377 radians per second, and delta Vmax is 150 volts. Determine the inductive reactance, the capacitive reactance, and the impedance of the circuit. So first, the inductive reactance, chi sub L, is just omega L. So we plug in the values that we were given, and we get 471 ohms. The capacitive reactance is 1 over omega C, and again, plugging in these values, we get 758 ohms. The impedance is the square root of R squared minus chi sub L minus chi sub C squared. We plug in those values, and we get an impedance of 513 ohms. So next, find the maximum current in the circuit. Well, Imax is Vmax over the impedance, so it's 150 volts over 513 ohms, or 0.292 amps. What's the phase angle between the current and the voltage? Well, the phase angle is the arctangent of chi sub L minus chi sub C over Z. We plug that in, we get that the phase angle is minus 34 degrees. Find the maximum voltage and instantaneous voltage across each element. So the maximum voltage is just Imax times either R, chi sub L, and C, so that's 124 volts. It's the maximum voltage across the resistor. 138 volts is the maximum voltage across the inductor. And the capacitor has the largest voltage across it, 221 volts. So then the instantaneous voltages are going to be the maximum voltages, and for the resistor it's in phase with the AC source, so it's just sine of omega t. The inductor leads it, so it's cosine of omega t, and the capacitor lags it, so it's minus the max cosine omega t. Now here's another problem that I really like to work through to talk about the economics of AC power. Let's say I have an energy generating power plant, and it needs to deliver energy at a rate of 20 megawatts to a city just a kilometer away. If the resistance of the wires over the whole kilometer is 2 ohms, and energy costs 10 cents per kilowatt hour, estimate what it costs the utility company just to get the energy from the plant to the city. How much does that cost in the internal energy lost in the wires in one day? Commercial power plant generators commonly use 22 kilovolts in their generators, but they boost that voltage up using a step-up transformer to 230 kilovolts for transmission. So we're going to do it at 230 kilovolts, and then let's repeat and see what it gets if we just did it at 22 kilovolts, if they didn't step up the voltage. So first, we need to know the RMS current. That's going to be the average power over the RMS voltage. So the power we said we need to deliver is 20 megawatts, and we divide that by 230 kilovolts. So the RMS current in the wires is 87 amps. The average power lost in the wires is the RMS voltage squared times R. This power is different than this power. This is the power delivered to the city. This is the power lost in the wires themselves. So that's 87 amps squared times 2 ohms. That's 15 kilowatts. So the energy then is power times time. So it's 15 kilowatts times 24 hours is 360 kilowatt hours. And the cost is the energy, 360 kilowatt hours, and they charge us 10 cents per kilowatt hour. So it costs the utility company $36 a day to get the power from the power plant to the city. Now, what if instead of a 230,000 volts power line, we just used a 22,000 power line? So we're going to repeat now. So now we're dividing by a smaller number here. So now that the power in the wires would have to be 910 amps. So if we plug that in here, we get that the power dissipated by the wires is now 1700 watts. And the energy, which is power times time then, is 40,800 kilowatts. And then the cost of plugging that in turns out to be $4,000. It's a huge cost difference to transfer the power at a lower voltage. In fact, if we were to repeat this and look what it would be at, say, just at 110 volts, there'd be several things. Number one, you probably couldn't push that power through the wire without melting it, because the current would be so high. Number two, the cost would far exceed anything that you would recover from selling the power. So the reason we transfer power across country at high voltage at 230,000 volts is to reduce the current in the wires and therefore reduce the energy loss. And then even through a city, typically power is delivered at 22,000 volts, and then when it gets close to the houses, there's another transformer that steps it down to the 110 volts that we have in our AC power outlets. So let's review what we talked about today. We talked about AC circuits. We saw that the voltage across elements can vary in both magnitude and in phase. We talked about such things as reactance, impedance, and phase factors, and quality factors. We showed how to solve problems using phasors. And we talked about certain AC circuit devices, such as transformers and rectifiers and lots of other things.